Hey there, astronomy students. This is Ms. Ruark. This is Vodcast 11.1, where we're talking about how stars are formed. All right, so we know that the life cycle of star, we've started doing some research on this, and we know that we have stars are born in nebula, which is groups of cloud and dust in the interstellar medium. Okay, we can have young stars here, which are being shown up by the brightness. They're still cloudy looking though, so that means that they're still in their birth process. We have these big, huge ones that are blue. These are your aging supergiants, your blue supergiants. They're very hot, right? And then you have these dense little clouds here, these globules or clouds of dense dark matter. Well, not dark, it just looks dark because it doesn't allow visible light through, which is where possible stars could be forming in the future. All right, so as we've stated, stars are born from the gas and the dust of the interstellar medium. Okay, so what are giant molecular clouds? Well, here's an example of a giant molecular cloud. This is Barnard 68. This is seeing it through visible light. It's very dark, it's very cold, and they're very dense clouds. They obscure the light of the stars behind them. So see, if you look at visible light, you can't see anything behind it. Well, what if we were to look at it through infrared light? Well, looking at it through infrared light here, we see the visible, or the lights that are coming through behind it. So it's not visible through visible light, and I'm using visible a lot, sorry, but you can see through it with infrared light. So these giant molecular clouds, this is where you can have some star formation. Okay, what's going to happen is these clouds are going to collapse. They're going to condense. Okay, let's see. Their size is about 50 picometers, 50 parsecs. Their mass is pretty big. Their temperature is a few kelvins, so it's not very hot, and they have very dense cores. Okay, so just some information here. They're much too cold, and they are too low in density to ignite these thermonuclear processes, which means that they are coming together to fuse hydrogen. They need to contract and heat up in order to form these stars. So what happens? Well, the gravity of these giant molecular clouds will make them condense and contract, but they are resisted by the thermal energy, the little bit of thermal energy that they do have in them, and so they need to be compressed by passing shock waves. Okay. So here it says that the factors resisting the collapse of a cloud. So what's some reasons that they won't collapse or won't condense in and form that thermal, the energy needed to fuse the hydrogen? Well, they might have too much thermal energy, which increases the pressure. Their magnetic fields might not allow it. Their rotation or angular momentum might not allow it, and they might have some turbulence from solar winds. Okay, so you need an external trigger to collapse the stars. So what's that external trigger? Well, a shock wave would be an external trigger. Okay. So here shows an example of a shock wave that comes through, and the shock wave will, and this just shows you the formation of it. The shock wave comes through, it approaches the interstellar gas cloud. As it passes through, it'll compress that cloud, and with the compressing, it continues to kind of move, and some areas are contracting more than others. So the dense part of the clouds becomes becomes the part where it's going to contract and pull in on itself. And in these parts here, you'll see where you have star formation starting. All right, so what are some sources of shock waves? What's a way that a shock wave can be triggered? Well, previous star formation can trigger previous star formation, so a star that was just made can actually trigger a shock wave to happen. So a supernova, explosion of a massive star, could actually trigger a shock wave that would go through. So if a really young star dies, really big young star dies, a supernova will shock wave through and contract some of the nearby gases. Okay, so supernova. Let's see, if you have ionization fronts of hot massive O and B stars. Okay, so those massive stars massive stars die. The O and the B stars will be born near where that happened. Okay. Another example of that would be if you had two giant molecular clouds that collided together. and that does happen sometimes. And then another one would be from the spiral arms in the galaxies, like our Milky Way. So the spiral arms are rotating, and when they rotate, they produce shock waves. All right, so and it says on your paper, the cold gas of interstellar space heats up as it contracts because the atoms fall inward and pick up speed. And astronomers say the gas is converting gravitational energy into that thermal energy. Okay, so see here, it's rotating. Rotating, rotating. Okay, protostars. All right, so protostars are the pre-birth state of stars. In these protostars, the hydrogen has not begun to fuse into helium just yet. It hasn't, it's just not there yet. Okay, so what it is, these protostars, these pre-birth state of stars, are in cocoons of dust, which means that the star is pulling together, it's heating up on the inside, but it's surrounded by this, well, cocoon. It's surrounded by all of this dust, so you can't really see it in if you looked at it through visible light, but if you looked at it through an infrared detector, you would be able to see it. Okay, so it's the pre-birth state of stars, and it forms deep inside of these dusty cocoons, not directly visible at visible wavelengths. Okay, begins as a cloud of dust, and as the protostar contracts, it starts to heat up. Well, let's see, where's my mouse? My mouse out, there we go. Okay, so here, protostar begins as an visible contraction of gas deep inside the cloud. Look how here the temperature is really low. Okay, as it continues to contract. See, protostars glow in the infrared. Contracting protostar grows hotter, but is hidden inside the dusty cocoon, and you can only detect it in the infrared. Well, as this freefall contraction happens, it starts to heat up. The newborn star becomes visible because it's going to spin. It's going to blow its dust away. All right. We can also get protostellar disks, and these protostellar disks are birthplace. Well, they believe they are birthplaces of planets and moons. Okay, so same thing. It's a cloud of gas and dust here, and it's spinning and it begins to contract on itself because of gravitational momentum. Okay, the conservation of angular momentum spins this cloud, and it's going to get faster and faster, and it's going to flatten out. Okay, now if you can't remember angular momentum, think of the ice skater. Okay, if the ice skater has her arms out and her legs out, she'll spin slower. Once she starts to contract and she pulls her arms and her legs in, she spins faster. And that's what's happening to this cloud here. As it continues to spin faster and faster, it grows into a protostar here at the center, and it has the disk of gas and dust around it. Okay, so it flattens out. And then sometimes these protostars, as they're spinning and spinning, they start to release this, I guess you want to call it a jet, right? A jet, and it releases it to the right and the left. It won't release it through the flattened part, but through, I guess, the top and the bottom, if you're thinking that the flattened part goes side to side. But if you look at it this way, it comes out from the part that's not flattened. Okay? And this would make what we call a Herbig-Haro object. Okay? Herbig-Haro objects are places where the brightness is variable. Okay? And it makes these things when the jets strike through, right here, interstellar medium. Okay, so here's an example of a Herbig-Haro object, HH34. Okay? And here's the jet that's being sent out. Again here, the jet that's being sent out. And there's another one here as well, cross-section of HH30. So here's your star here, and it's spinning. Here's the flatness, and it ejects out this jet. As you see, it comes out. And here's an example of it. This, of course, is a diagram. And then this one is where you have the visible light, or I think this one actually is in IR. All right, so from protostars to stars, so what happens here? Well, we have our birth line here, which is where all your protostars are going to start, and as it sheds its cloud, it's going to probably come over here to the main sequence. You have stars over a few solar masses that'll reach the main sequence up here, and the less massive stars will continue to contract and contract until they shed their dust, and they get a little bit more massive, and they make it to the main sequence here. Okay. Yeah, I just did that. All right, so evidence of star formation. Well, in in this constellation or this star, we have nebulas that arise. They contain many massive, very young stars, including T Tauri stars, which are strongly variable and bright stars in the infrared. We also have in the Cone Nebula, young, very massive star here. Okay, and this picture here is from this little cross section right there. Okay, in the optical, we can't see it, but in the infrared, hey, look at that. And then look at all these little star formations here that are going on at the same time. Okay, smaller sun-like stars. Okay, and then in the, oops, go back. Yeah, haha. All right, and then here's another star-forming region in this nebula as well. There's a bunch of little stars that are forming in there. Okay, all right, and I'll see you in class.